Thank you very much. So today I'm going to present some of the work that we've been doing in Huawei in terms of developing a mixed precision iterative solver and to implement it within OpenFOAM. And I'm going to show you results regarding accuracy and efficiency of the overall approach. So I'm going to briefly go over the motivation of the work and then present also briefly the approach that we're using. I'm going to talk about the coupling within OpenFOAM and, like I mentioned, the results showing the overall accuracy and the overall efficiency of this approach and the ongoing work to further improve and expand this work. So why mixed precision computing? So I'm going to briefly go over this. Some of you may be familiar with this. This is a graph that, if you're familiar with HPC, you would be familiar with this Moore's law. And this graph was presented a month ago at the International Supercomputing Conference in Hamburg. And basically shows the trend for the past 50 years in terms of increase of computing power that is available. So originally the idea was Moore's law is like you would have some kind of linear improvement over the years, but what we see for the past 10 years is that you're reaching a plateau in terms of frequency of the CPUs you're using, the performance, the single thread performance, et cetera, meaning that if you want to keep getting more and more out of the coming computers, just waiting for the power of the CPU to keep increasing is not going to be enough. So how to still improve the performance of your solvers, like based on modern architectures, is one way is to use accelerators. And there are many different types of accelerators available out there. And typically, a lot of the powers of those accelerators come from low precision computing. So either FP32, even FP16 in some cases. So meaning that if you want to be able to get the most out of those accelerators, you need to be able to do your computations in lower precision. And that poses some problem because for many scientific applications, including OpenFOAM, a lot of the users are not willing to pay the cost of reducing the overall accuracy of the simulations just to get the results faster. So you need to find a way to somehow offload the work to those accelerators without losing the overall accuracy. And this is also a table coming from the International Supercomputing Conference showing that the mixed precision benchmark showing that the speed up on the top 5 supercomputers, speed up between the HPL benchmark run on single precision, on double precision, but just one precision, or versus mixed precision. And you can see that in a lot of cases, you can get up to 10 times speed up if you're using the mixed precision algorithm efficiently. So traditional HPC, you could think of like using high precision computation. Modern HPC, if you want to be able to use as much as possible the capabilities of even modern CPUs, but also accelerators, to use as much of offloading to lower precision as possible. So like I mentioned earlier, one of the challenges is that you don't want to lose any of your accuracy. So you want to offload the work to low precision, but recover as much as possible the accuracy that you would have got if you were using double, for example, in this case, double precision computations. And so by offloading a lot of the work to low precision, you get acceleration because low precision arithmetic is usually more computationally efficient, so you can reduce the overall simulation time by doing that. And you're having less communication. So if you're looking at large-scale simulation, the more work that you're doing in low precision, the less data you have to communicate between nodes, for example. And so you're also gaining some time by reducing the overall memory there. And if you look at mixed precision computing today, Most of the works are based on, for linear solvers, for example, doing iterative refinement to use a solver, do iterative refinement to convert slowly to the desired accuracy that you are targeting. For nonlinear solver, there's not a lot of work available out there. Most of them requires linearization to be able then to use the typical iterative refinement approaches. So our approach is to use a defect correction algorithm, based algorithm. That defect correction term would drive the solution slowly to the accuracy that we're looking for. So I'm going to not go into too much details about the algorithm, but I'm happy to discuss more after that as well. So the idea is that we start from a given set of PDEs. It can be heat equation, it can be Borges equation, Navier-Stokes equation. And then no matter what you're doing after discretization, you get to a system AX equal B. In this particular, at that stage, I'm not making an assumption on A. A can be a linear or nonlinear operator that is applied to X. X is the solution that you're looking for. B is a given right-hand side vector. And what we define here is the defect correction term. So basically, the residual of your equation is always defined as the difference between AX and B. X tilde here being the current iteration, the current solution that you have at the current iteration. So R is basically the error between AX and B using X, like the most updated X that you're having in your solution. And what we define as the defect correction term is basically the difference between that residual computed at low and high precision. So what that term gives you is an indication of the error introduced in your system by now doing part of the computation in low precision versus what you would have got in high precision. Then during the stage where you're offloading some of the computation to the low precision device or even on the CPU to lower precision, then we add this additional defect correction term to the right-hand side of the equations that you can then show that upon convergence of this equation, then you would recover the original equation on high precision. This is an iterative process. You still have to do back and forth between high and low precision to update this defect correction term. So there is a sweet spot between the convergence that you're trying to get in low precision before coming back to high precision to update this new defect correction term and to go back again. So this is how the algorithm looks like. You start from a given set of equations, like I said, initial guess. Usually we try on the high precision device to use as cheap of a solver as possible to update the initial guess to help a little bit the convergence. We compute the defect correction term. We offload to low precision the solving the part of the modified system equation with the additional source term on the right-hand side. We go back to high precision, correct the solution, compute the new defect correction term, and loop again until we reach the overall convergence that we're looking for. I'm going to show some initial results, like the first implementation of this algorithm that we obtained. So before going to OpenFOAM, we started with a nonlinear Poisson equations with just one equations. We used the manufacturer solution to get an exact solution. It was easier for us to understand the behavior of the overall approach. We solved this problem on a 64 square grid in 2D. And we were trying to reach FP64 accuracy results. So on the graph here, I'm plotting the residual as a function of the number of iterations. In blue, we have the pure double precision simulation. So that's our reference. That is the best results that we could expect. And that's the target that we are trying to get. In light blue here, we have like the result we obtain is only in single precision. And in green, we have only in half precision. So in that case, in those two cases that you get the typical plateau that you reach when you reach the machine precision accuracy, basically in single and half precision. And in yellow was the result that we obtained with the mixed precision double and single precision together, FP64 and 32 together. And in red is what we obtained when we did the initial implementation with FP64 and FP16 together. So first of all, with single precision, we saw immediately that there are a benefit. The number of iterations that you need to converge is higher because you're basically offloading a lot of the work to lower precision. You need to do a little bit more cycles, but you need to take into account that each of the cycles now is much cheaper because it's happening. Like the computation itself is much cheaper. You know, if you think about larger scale, also the communication is going to be more effective, etc. For half precision, we were having some issues, and then what we realized that in very low precision, like half precision, you need to take care of additional issues coming from underflow, overflow, and you also have an issue where the defect correction term on the right-hand side that you're adding is becoming smaller and smaller as you're converging. And it gets so small that eventually the difference between the right-hand side B and the defect correction term becomes not something that you actually can see in half precision. Like the difference becomes negligible. As far as the solver is concerned, D is 0, and then there's no effect anymore. So we had to do on-the-fly rescaling as part of the algorithm. Once we reached to under a certain threshold for the defect correction to always become like having some kind of effect on the convergence. And when we have done that, we obtained the pink curve that was giving us now the convergence all the way to double precision convergence. So that was like the initial implementation, not within OpenFOAM as a standalone solver. And it really helped us figuring out, especially for very low precision, all the effort that had to be put to really get good results in very low, when you're offloading to a very low precision device. We did additional test case before going to OpenFOAM. We wrote 2 different standalone 2D solvers, one that mimics the predictor corrector approach similar to SimpleFOAM in OpenFOAM. So this one was actually for explicit. So we set it up. We use high-order numerical methods because we wanted to really understand the effect of the mixed precision only and not combine with numerical errors. We run the 2D double shear layer case. And then we saw that when using only half precision simulation, we would really get some kind of a dissipation effect that was very different from the well-refined FP64 simulation. And when we added the mixed precision on top of this, then we managed to recover the same results as the FP64 simulation. And then we also ran the 2D lead-driven cavity. So again, that case, it's very similar to SimpleFOAM now. Like we are solving momentum and the pressure equations one after the other. And what we showed is we managed with the mixed precision solver to recover the convergence that we would have obtained with FP64. And we also compared the results with experimental data. And that was, at this point, the main aspect of the research was to show we can recover the accuracy. Now, the next step was to see within OpenFOAM what is actually the benefit of doing that. Now that we know that the accuracy can be recovered, we want to make sure that now it adds some benefit in terms of efficiency. So before I show the results very briefly, so OpenFOAM, everyone is familiar here in this session. In order to implement our solver within OpenFOAM, we use the Ginkgo library. So you heard earlier PETC for Foam and PETC, there are other libraries available. Ginkgo is another one. Ginkgo is a high-performance linear algebra library that is designed to be able to offload also a lot of the work to accelerators, but works also on CPU. And the important thing for us is that the Ginkgo has what's called OGL, which is basically a layer that allows you to couple Ginkgo with OpenFOAM directly. And basically, we decided to use that so that we don't have to do any of the work to couple our approach to OpenFOAM directly. So now I'm going to show you the 2 different test cases that we've tested this approach on. The first one is the 3D lead-driven cavity case. So it's a 3D steady-state laminar test case. We tested several mesh sizes to be able to see the benefit of the approach for different mesh sizes, 2 different Reynolds number, 100 and 400. And we also have data to compare to. So the first thing, again, it's very important for us to show that the accuracy is recovered, because without the accuracy, there's not a lot of benefits to show the acceleration. So on the graphs at the bottom, basically, after convergence, we looked at velocity profile compared to the experimental data that were available online. And we showed that we had a very good agreement with those experimental data for both Reynolds numbers. And these are the residual convergence. So I'm just going to take 1 minute to go over the different curves here. I mentioned in the previous slides when we talked about the very low precision device that like we had to take to add additional capabilities as part of the algorithm, rescaling, but we also worked a lot on error tracking, so that some of the or round-off error and truncation error that happens when you offload the work to low precision device would be already taken into account, tracked, and then already pre-added to the solution every time you go back to the high precision device, and that allows like to recover a part of the error. So for example, the blue line is pure single precision. The green line is also pure single precision with no mixed precision, but with error tracking. You can see that you can already drop a little bit of the error there. And then mixed precision with the error tracking together is the red line, and that light blue line here is the reference for that case that we obtained with double precision. So we still have a little bit more to get to pure double precision, but we already have 4 order of magnitude reduction compared to pure single precision. And we measured the acceleration. So we used Huawei's Kumpen 920 CPU. So it's an ARM-based CPU. One of the characteristics of the CPU is that very large cache compared to other CPUs. So it was important for us to evaluate the benefit of that for this approach. And on this figure, I'm showing the efficiency of the acceleration and the efficiency of the approach. So the top 2 lines show the speed up that you get by running the solver purely in single precision compared to double precision. So you get about close to on a full node utilization, you get close to 2x speed up when you're using pure single precision compared to double precision. The mixed precisions results are the 2 bottom lines. So we get about 1.5x speed up when you're using full node utilization, which shows about 80% efficiency compared to the single precision. So what's important to remember is that we get 80% efficiency compared to the single precision, but with the accuracy much closer to the double precision simulation. So those were the results that we obtained for the 3D lead-driven cavity, and we wanted to tackle a case that is more complex. We looked at the Audi driver test case. So that test case is an industry standard benchmark, so it's available. You can download it online. It's widely researched. It's also part of the ExaFoam, one of the test cases, part of the ExaFoam project. Numerical setup, incompressible turbulent flow with KM omega SST Reynolds models. Reynolds number is about 8.7 10 to the 6. And again, we use simple foam. In this case, we didn't do the ping-pong foam, but the results I'm going to show in the next slides are coming from a simple foam simulation. I'm showing, again, first the accuracy of the approach. I'm showing on the top is the residual convergence at each of the time steps. So we basically have in green the convergence for single precision, and then red and yellow lines show the convergence for the mixed and double precision. And that shows a good agreement between the 2 solvers. And at the bottom, we have the drag coefficient convergence that shows that there is a slight oscillations that are different between the double precision and the mixed precision, but overall, the plateau that is reached between 2 simulations is in a good agreement, and also in good agreement with published data that is available in the literature. And in terms of acceleration, using the mixed precision showed an acceleration of about 1.4x compared to pure double precision. So we managed, for example, to recover drag prediction for this particular test case, but with an acceleration of about 1.4x. So I'm going to summarize this presentation. We developed a mixed precision defect correction method that is suitable to solve linear and nonlinear equation, at least nonlinear equations for example, single precision, double single precision that works. For lower precision, there are still some issues to be taken care of. Implemented and tested the method within the Ginkgo library. So we used the Ginkgo framework to be able to couple that approach to OpenFOAM using the OGL framework. We tested it for 2 different test cases, the 3D lead-driven cavity and the Audi driver case. We demonstrated 1.4x speedup with 80% efficiency compared to single precision for the lead-driven cavity case, and about for both cases near FP64 accuracy recovery using the mixed precision. And as part of the implementation, there's a lot of work that's been done in terms of error tracking and rescaling to improve the accuracy and the efficiency also, how much convergence you can get for each cycle that you're doing in low precision. And now we're focusing on improving even more this error tracking using uncertainty quantification, for example, and to expand this approach to more solver. Like in this particular study, we targeted the CG solver, but now we are extended to more solver and preconditioner as well, and to test 2 more test cases. And thank you very much.